Okay, we're gonna learn how to apply the principles of static equilibrium of uh, multi-particle systems, so large bodies or bodies which can be modeled with more than one particle. All right, so uh, the principle, just to recap, recall the principles from the previous lectures. So here I look at all the external forces in the body, and this is a vector equation. So this is a vector equation, and so we usually look at components over here, and then this is also a vector equation because we look at the directions of the torque. So let's say only look at the external forces. All right, so we're not going to look at internal forces, and later on we're going to discuss these internal forces, but right now this will be all external. So here is a board that's of mass m, and there is a support here. So there is a support upon which the board is. So if here is a board and here is a support, if you can see that if this was only the case, then the gravity, the weight of the board will act at the center of gravity, right? And then there will be a normal force from here, Fn. They will appear, if this thing is not accelerating, then this appear, they may have some values, I don't know if they're equal or not. If this is the only thing, then you will find that this thing will rotate, and some point later the board will be maybe in that direction. Center of gravity will come down here, right? So it will actually accelerate. Center of gravity or center of mass accelerates. So if there's nothing else over here, then acceleration of the center of mass of the board is not zero. That means it's not in equilibrium, non-static equilibrium. Okay. So this is the intuition we bring into the over here. So what this board has some weight sitting on this side, and it is claimed to be in a static equilibrium if the distance d is correct. So given m and l and m, so we're supposed to find, given m, l and m, find that critical distance that I should place this block at. Okay, so it's not necessarily at the very end, but right now I have placed right at the end. Okay, just for the simplicity, so that all these formulas will be simpler to write. But we'll do another example where you can place anywhere, and you have to find where it should be. All right, so basically we're trying to figure out where should I put the support. Where should I put the support from the one edge where I place this block so that it's in equilibrium? So that's the question we want to answer. Second question we want to answer is what will be the normal force at that time, and if you said normal force will be just the weights, let's see if that's correct. Okay. Okay, so if I look at this question, so I like to try to see this this equation first before I do that. From this picture, it seems like when I have intuition this way, then my physics intuition will say, hey, this weight of this thing, little mg, will act on the board at that point, and the gravity of the board will act at the center, and the normal force will act at that point. So I identified these three forces, but I also see that as far as figuring out this distance is concerned, well, I don't need to worry about this force, because this force will not be tipping things. So this trying to rotate, and this guy is trying to balance that way. So it looks like a torque type of balancing, right? So we can directly go in there and see what we get from here. So we have, well, we can pick a pivot point. So say if I pick a pivot point, then right away it seems we have a picture. So torque of big mg is counterclockwise, and if this is d, then the lever arm for this is L over 2 minus d. So big mg times L over 2 minus d, and this is clockwise, right? So this can be, I put a minus there. For the other little mg, for that force, the torque, this is the line of the torque, and the distance is, lever arm is d, so little mg, little d, and this is counterclockwise. So if I take this positive, this will be negative, and the torque of this will be 0. Torque of Fn will be 0. So if I add these guys, I get tau external net, that should be 0, and this side, let's take this plus, then this will be minus. So I got mgd minus big mg L over 2 minus d equal to 0. And I can rearrange it. Of course, g kind of cancels out from here. So this d will add to that d, because this minus was plus, so 2, not 2, as m plus big M, little d, and this can go on the other side, ml over 2. So the d is m over 2 times m plus big M times L. I didn't even have to use this to find that. To find a normal force, I will have to use that. Okay, so let me illustrate the use of, in this problem, the use of, so if I, so just by doing that, I got that. By doing that, I will have, well, all the forces along the y direction. So I can take this as a y-axis. So I get a Fn, y component. This little mg is y component, and this big mg is y component. So this is Fy equal to 0 gives me this equal to 0. And so the Fn is simply little m plus big M times g. So this equation only gave me one equation because all the forces were along one direction. Now the forces are along x and y direction, then I will have to work out both the x and y components. Okay, done with this example. Maybe I'll do some other examples in another video.